In the previous lecture, we have discussed in very detail the quantization of Schrodinger field for system of bosons. Now today our aim is to discuss the same problem for the system of fermions. Okay? You know that fermions are the particles obeying the Fermi-Dirac statistics, and these particles have half integral spins. When you say that fermions have half integral spin, that means the spin of fermions are actually either h bar by 2 or 3 by 2 h bar or 5 by 2 h bar and so on. Okay? And you also know that these fermions obey the Pauli's exclusion principle. And according to Pauli's exclusion principle, any quantum state cannot contain more than one fermion. Okay? So, in fact, if we have to fill up the different quantum states by fermions, that means any quantum state will either contain no fermion or at most one fermion. Never more than one fermion can be in the same quantum state. And that's why you have seen in case of boson that the eigenvalue of the number operator, which we have denoted by the symbol this nk, this is eigenvalue of the number operator nk hat. This was actually 0, 1, 2, 3, so on up to plus infinity for bosons. We have seen, okay? This was for bosons. But as in case of fermion, you can see that according to Pauli's exclusion principle, in any quantum state will be either no fermion or at most one fermion. So, in other words, you can say that any state can occupy either 0 particle or 1 particle. So, you can easily think that the eigenvalue of the number operator nk hat will have only two values in this case. And those two values are what? Those two values are either 0 or 1. Okay? Either 0 or 1. So this is the basic difference. In case of bosons, you have seen that the eigenvalue of number operator nk hat is in fact from 0 to infinity at a step of 1. So you have seen that any number of bosons can be in the same quantum state. Okay? But here, since there is a restriction that in a particular quantum state there will be either no fermion or at most one fermion. So this so you can say that nk, which is the eigenvalue of operator nk hat, which is a number operator, that can have only two distinct values, either 0 or 1. Okay? So the commutation relation obeyed by the two operators which we have called in the previous lecture the annihilation operator and the creation operator. And you know that annihilation operator is denoted by the symbol ak hat and the creation operator by the symbol ak hat dagger. Okay? Actually, these two operators were satisfying some commutation relations, okay, in case of bosons. But here, in the same manner, in the same fashion, according to Jordan and Winger, these two operators will satisfy not the commutation relation but anti-commutation relation. Okay? So in this case, these two operators ak hat and ak hat dagger satisfy the following two anti-commutation relations, not commutation relation. You can see that the anti-commutator, you know that this curly bracket represents the anti-commutator. So anti-commutator of ak hat and al hat dagger this is equal to the anti-commutator of AL hat dagger with AK hat, and that is, you know, that this is an anti-commutator, so this can be written as AK hat AL hat dagger plus AL hat dagger AK hat, and that is equal to delta KL. You know that this delta KL is the Kronecker delta, and this delta KL, you know, this will be equal to 1 if K is equal to L, and this is equal to 0 when K is not equal to L, you know. Okay. And the other anti-commutation relation obeyed by these two operators is given like this. This is anti-commutator of AK hat with AL hat is equal to 0, and at the same time the anti-commutator of AK hat dagger and AL hat dagger is also equal to 0. Okay. And actually from these two results you can easily find that if our aim is to obtain the anti-commutator of AK hat with AK hat, okay, AK hat with AK hat, then that will be equal to what? That will be AK hat times AK hat and plus AK hat plus times AK hat, and this will be equal to 0, and so 2 AK hat equal to 0, and so you can say that AK hat is equal to 0, and in the similar manner this AK hat dagger times AK hat dagger is also equal to 0. Okay. So from this equation 1 it is evident that this result will also hold, that AK hat is same as that AK hat dagger, and that is equal to 0. In fact, as in case of bosons, we have seen that these two operators in these relations are referred at the same times. In the similar manner here you can also say that all the operators in these relations refer to the same time. Okay. Now when we will use these relations, we can easily see that the square of the number operator, that is nk hat square, will be simply equal to nk, because the eigenvalue of nk hat is either 0 or 1, and you know that a square of 0 is also 0 and a square of 1 is also 1. So from this you can easily say that the operator nk hat square is equal to nk hat. Okay. And when you will take this nk hat in LHS, then you can write this expression like this. This is nk hat times nk hat minus 1 equal to 0. So if we consider any arbitrary state, let us say denoted by the symbol phi k, and when we will operate this operator nk hat times nk hat minus 1 on this phi k, the result will be simply 0. And from this you can easily see that the eigenvalue of this nk hat will be either 0, or from this operator nk hat minus 1, the eigenvalue of this operator will be equal to 1. So you can say that this nk, which represents the eigenvalue of the number operator nk hat, that is either equal to 0 or equal to 1 for any value of k. It means you can say that this n1 hat, sorry, not hat, but n1, if k is equal to 1, then you will write it n1. That n1 will be equal to either 0 or 1. Okay. Similarly, n2 will be either 0 or 1. Okay. So for all values of k, this nk is equal to 0 or 1. And so you can see that since the values of this operator nk hat is equal to either 0 or 1, so it is evident that the commutator of the operators nk hat and nl hat will be equal to 0. Okay, and actually this result refers that the base vectors can be characterized as simultaneous eigenfunctions of the number operator nk hat. And in this condition you can also say that nk factorial will be equal to 1. Why? As you can see that nk factorial means what? Nk factorial means 0 factorial or 1 factorial, but you know that 0 factorial is equal to 1, or this 1 factorial is also equal to 1. So nk factorial, this will be simply equal to 1. Okay. Now actually from this relation we can obtain the very important relation which we have seen in the previous lecture. So I have written it directly here, that the state denoted by kth n1 n2 so on nk is equal to a1 dagger to the power n1, a2 dagger to the power n2, so on, ak dagger to the power nk, and this will be operated on kth 0. You know that kth 0 actually represents the ground state wave function. Okay, ground state eigenfunction. Okay. Now as you can see that all the ak daggers operator actually anti-commute, and as these operators ak dagger anti-commute, so definitely there will be a phase factor equal to plus minus 1 undetermined in this equation, unless we specify the order in which these operators operate. Okay. In fact, if you write this equation 4 in such a manner that the superscripts n1, n2, so on nk are actually in increasing subscript, order of increasing. In fact, then we have to put plus sign. Okay, when the creation operator, that is ak hat dagger, will be operated on it. So I have mentioned it here. You can see that we put plus sign when the creation operators are arranged in equation 4 in order to increasing subscript. Okay. Now actually in the previous lecture on system of bosons we have obtained a very important result. So on the basis of that derivation I have written that result here directly. Actually in the first part of this lecture on system of bosons we have derived this result, but here I am quoting or here I am writing this result directly. You have seen in the previous lecture that when we operate ak hat to the power r times al hat dagger to the power n on the ground state function kth 0, then our result is what? You have seen in the previous lecture that this is equal to n factorial divided by n minus r factorial ak hat dagger to the power n minus r operated on this kth 0 delta kl. Okay, and from this result we can easily find that when we operate the operator ak hat, which is actually annihilation operator on this state, that is kth n1, n2, so on nk, that will be equal to minus 1 to the power n1 plus n2 plus so on plus nk minus 1. a1 hat dagger to the power n1, a2 hat to the power n2, and ak hat dagger to the power nk operated on k0. Okay. And if we consider that the sum of these n1, n2, so on nk minus 1 is equal to sk, then we can write the eigenvalue equation like this. This is minus 1 to the power sk and nk of, and the eigenvector is n1, n2, so on nk minus 1. Actually here this sk has been written at the place of sum of n1, n2, so on nk minus 1. So you can see that this sk is equal to sum of all n1, all n, and so we can write it that this is summation over r 1 to k minus 1 n r. Okay. Now if instead of this annihilation operator ak hat, you will operate the creation operator ak hat dagger on the same state, that is the state represented by ket n1, n2, so on nk, then what will be our result? You can easily write that result on the basis of the result which we have just obtained. So in this case, actually at the place of the eigenvalue nk, here we will have actually this 1 minus nk. Okay. So ak hat dagger operated on the state represented by ket n1, n2, so on nk. This is equal to minus 1 to the power sk, 1 minus nk, and ket n1, n2, so on nk plus 1. Okay. So you can see that when our operator is ak hat dagger, actually in that condition here the eigenvalue of the number operator is nk plus 1. So you can say that even in case of fermion, this ak hat dagger is recognized as a creation operator because its operation increases the eigenvalue by 1. On the other hand, you can see that when we operate this operator ak hat on the state represented by this ket n1, n2, so on nk, then the eigenvalue of the operator is actually nk minus 1. It means the eigenvalue is decreased by 1. So this ak hat is recognized as annihilation operator even in this case of fermion, as it was recognized in the case of bosons. So this recognition in case of bosons and fermions are same. Okay. So even in case of fermion, you can say that this ak hat is an annihilation operator and this ak hat dagger is a creation operator. Okay. Again you can see that when we operate the operator ak hat, the eigenvalue is nk, and when we operate this ak hat dagger, then it is in fact 1 minus nk, as you can see it here. So in this case you can easily see that if we take nk equal to 0, then we cannot further decrease the value of this nk. So this this result shows that a quantum state which does not contain any fermion cannot be amplified further. It means if there is no fermion, then it cannot be amplified further. On the other hand, if a quantum state contains one fermion, it means you are taking the eigenvalue of our number operator nk hat, which is nk equal to 1, then it cannot be further filled further phase. And this is the property of fermion, that a quantum state will be either empty or it will contain at most one fermion. Okay. So you can see that this is the basic difference in case of bosons and fermions. In case of bosons, we have seen that nk has a value running from 0 to infinity at a step of 1. So you have concluded that actually in that condition any number of bosons can be in the same quantum state. But here, if an state is empty, it cannot be further emptified, and if a state contains one fermion, you cannot increase the number of fermion in the same quantum state. Okay. Now, let us see this equation number 6 and this equation number 5. When actually we will combine these two equations, that is equation 6 and equation 5, what will be our result? You can see that in this combining those two results, we can see that when nk hat will be operated on the state represented by kth n1 n2 so on nk, our result will be what? This will be nk and nk and the same eigenvector is n1 and kth n1 n2 so on nk. Okay. But this result will hold only when you can say that the bra n1 bar n2 bar and nk bar nk hat kth n1 n2 nk, that is equal to nk delta n1 n1 dash delta n2 n2 dash delta nk nk dash. Actually this result I have written on the basis of the previous lecture where we have actually derived it. Okay. So up to this you have learned that in any quantum state no two particles having the half integral spin can be accommodated. It will be that quantum state will be either empty or it will contain only one particle. Okay. And this is the basic property or basic feature of fermion. Okay. Now actually in this case we will see, you can see that the two operators, that is psi hat and pi hat, you know that this psi hat actually is just analogous to the position operator, and this pi hat is actually the conjugate momentum operator. Okay. Or the field operator. Actually these two operators satisfy the some of the anti-commutation rules which I have written here without any proof, and so you have to remember it. So anti-commutator of this psi hat and psi hat dagger, this is actually equal to summation over KL, and anti-commutator of AK with AL dagger, UK of R, UL of R dash, and that is equal to Dirac delta function delta R minus R dash. You know that this is actually the three-dimensional Dirac delta function. Okay. Three-dimensional Dirac delta function. Okay. And the another commutation relation obeyed by these two operators is what? This is anti-commutator of psi hat of RT and pi hat of R dash T, that is equal to IH bar delta R minus R dash. This is Dirac delta function, and I hope you have an idea of Dirac delta function, and I have also discussed this in the previous lecture. Okay. Now actually these results does not resemble with the Heisenberg relations, commutation relations, but in case of bosons these two operators obey the commutation relation which is just equivalent to the Heisenberg commutation relation. So in contrast of boson, in case of fermion the commutation relation obeyed by these operators psi hat and pi hat actually do not uh, do not are not actually equivalent to the Heisenberg commutation relations. So I have mentioned it here that you can see that these relations have no similarity with Heisenberg relations in contrast with the system of bosons, because system of bosons obey the commutation relation which is just similar to the Heisenberg commutation relation, but this anti-commutation relation obeyed by the operators psi hat and pi hat in case of fermion does not resemble, are not just analogous to the Heisenberg commutation relations. Okay, so this was all about the system of fermions. So you have seen that actually in 3 lectures we have completed the second quantization of the Schrodinger field or non-relativistic field. Now in the forthcoming lecture we will see the second quantization of relativistic field and the electromagnetic field. Okay, so thank you very much.